Hi, my name is Camila Samana, and this is my Physics Lab 4 on oscillations, where I'll be talking about an introduction to the lab, important physics concept, the tracking model, the coding model, the results, and a comparison between both, and a few conclusions as well. So, this was a two-part lab that consisted first of the tracking model of the oscillating spring and the computational model of the tracker video. Then we had to compare the graphs of the change in spring energy, the change in gravitational potential energy, the change in kinetic energy, as well as the total change in energy. And we have sinusoidal waves and a horizontal total change in energy. We also had to compare the position graphs in both x and y directions of both the model and the experiment, which in the end were also sinusoidal waves that were nearly identical. Okay, so a few important physics concepts for this lab are the momentum principle of position of the formula, which we have seen like several times before, and the most important one is the energy principle, which says that the change in energy of the system is equal to the work done by the surroundings. In this lab, the system includes everything, the spring, the mass, and the earth, but there's nothing on the surroundings. So the change in total energy of the system is equal to 0. That means that there is a change of kinetic energy plus a change in gravitational potential energy plus a change of the spring energy, they all equal to 0. So here is the computational model, and the initial conditions were the initial position for the mass, which was obtained from the tracker coordinates. The spring constant for this specific spring was calculated from the period that is seen here on the tracker, and L0 was calculated from holding the mass at static equilibrium with the spring already knowing its initial position. And the spring constant, and we solve for those numbers, and you can see the results on screen. In the loop part of the code, we can see that we're trying to find the change in all the different energies and the change in total energy by making an iteration each time, the initial and final, so we can graph the energies, the change in energies. So here are my results. They're in the change in energy versus time graph, and we can see two almost identical but opposite sinusoidal curves for the change in gravitational potential energy and the spring potential energy, and they alternate with each other. And also a much more smaller sinusoidal kinetic energy curve and a completely horizontal change in energy. So it means that there was no change in energy at all. And here are the position versus time graphs in both the x and y directions. In the y direction, you can see that the model and the experiment were nearly identical, but in the x direction, there was a more larger difference because the amplitude of the sinusoidal wave of the experiment is smaller than that of the other model. So, I'm sorry about that. A few short conclusions. In the model, we can see that no work is being done in the system, which is why you can see that the change in energy of the system is equal to 0, and why we have a horizontal line across the graph. But in reality, some work is really being done by friction or air resistance, or really any other forces in the surroundings, which is why you can see the decrease in amplitude comparing the model to the actual experiment in the system. A few sources of error that could have come from this are human error when I was using the tracker system, as well as an error in recording the video and moving the system to be analyzed. So, to answer a few questions, first, is the energy principle satisfied in my computational model? The answer is yes, as there was no work done by the surroundings, so this can be seen in the change in energy equaling to 0 that is graphed in the model with an orange line across the horizontal x-axis. And at any moment in the graph, you can see that all of the other energies add up to the total energy being 0. Also, we're asked to compare oscillation periods in the x and y position graphs from the tracker, and in x, the oscillation period was 1.615 seconds, while in y, the oscillation period was 1.520 seconds. So the oscillation period was quicker in the y direction, and this can be explained as the system having more friction and the spring having more friction when going in the x direction, or other forces acting on the surroundings in the real world. Thank you.